The topic of this video is multiple regression in Excel. Uh, this relates to a previous video I did in which I talked about a linear relationship, a line that we could draw based on a scatter plot that represents the relationship between two different variables. However, in the real world, sometimes there are multiple things that we might use to predict some outcome. And so in a previous case, we talked about how much did it cost to run a factory in a given month, and then we only had one thing to predict that by, which was a single product. In this case, we have three columns of data, or three different variables that might be used to predict some outcome that's on an interval basis. Now, more broadly speaking, sometimes with regression we're concerned with predicting a 1-0 value. So sometimes we're want to know, for example, do you win or lose? Did you buy or not? So a couple different industry examples here. Basketball, did you win or lose? Energy, did you find some energy or not? Healthcare, did the person live or die? And so in other contexts, we just want like a 1 or a 0 outcome. 1, it happened, or 0, it did not. But in other cases, we just want some interval or continuous range of numbers. Maybe it's the amount of money we expect to earn based on a number of factors. Let's go ahead and demonstrate how you would create a regression using the data analysis tools within Excel. So if I click Data Analysis and I go down to Regression and click OK, I'm going to first grab the thing that I'm predicting, which is my cost, and then I want to select the variables that I'm going to be using to predict that cost in any given month. I'll add some labels and a confidence interval limit, even though I won't be talking about it. And then I need a place to put this data, so I will put it right here. Alright, so here's the outcome of the analysis that happens. There are a few different things that I would be looking for generally as a scientist. So one of them is the adjusted R-square, or either the R-square or the adjusted R-square, and either of these is an indication of how well our model, to what degree our model, meaning the input variables I selected, reflect the changes, how are these variables correlated to this outcome here. And a lot of we would say, with this was 1, we would say this perfectly, that my input variables perfectly predict the outcome. We could say maybe we predict about 64% of the outcome based on these variables. So it's not a perfect prediction, but I would say it's pretty good. In some sciences they like super high numbers, and in other sciences even a really small number is still useful to them. Another thing I would look at so also, maybe just mention one more thing. If I were to compare two different models, I might compare it based on this number and say, hey, one of the, if another model comes back with 70% and another one comes back as 30%, we can say that the 71% is doing a lot better at predicting this than the one that says 30. The next thing I would look at here is this area where we have this F-test conducted, and really what this is telling us is that from a statistical standpoint, does this model predict confident? Can we say that we're confident that this model is predicting some outcome, that it's just not just some garbage chance that our variables are associated with the outcome. This is our our degree of certainty. Anything lower than 0.05 is a higher and higher degree of certainty that we've got a good model, that it matters, that our input variables really truly do impact some outcome. So this kind of emphasizes the strength of the relationship and the degree of the relationship, but this is more about our confidence that the model is valid. As a scientist, usually the place I go to first, assuming that my model matters, is I go down here and I look for my variables. So A, B, and C are my variables, because it's not always the case that each variable matters in predicting some outcome. And so over here I look at my p-values and I'm looking for anything less than 0.05. That's my rule of thumb for something that matters or doesn't matter. And so my intercept matters, and that's kind of like a fixed point. If you're talking about like a point slope formula, that it's this thing that you add the rest of the numbers to. Anyway, that's just, we're going to use this fixed number over here as the minimum cost for running our factory, and then add in some factors based on the number that we've produced. The next thing is the p-value for A. At 0.23, we don't feel very confident that A mattered. However, we do think that the number of products of B that we make, since this is less than 0.05, we think that we feel highly confident that this impacts the cost of of running my factory in a given month. And same thing for C, because this is a low number, we're also confident that this particular variable or input affects the output there. And once we've created a model like this and we're sure that we have this output and we're sure that our model matters because it's significant, we can actually write a generic formula such as the following. I can say cost equals, and I'll go down here and I see 35.102.9. So cost equals 35.102.9 plus, and I've got this factor here, 2.065. 2.065 times, and I'll call it A made, plus 4.176 times B made, and then plus 4.790 times C made. Alright, so this formula that I've written there is a generic formula that we can then use to estimate what the cost of what this real cost is, and we can kind of compare and see how well we did. So let me go ahead and experiment with that. So I'll say so prediction, and so my prediction is based on this. So let's go ahead and use my formula, and instead of A made, I'll get rid of that and use the actual number, because A made was just a variable. Oops. For B made, I want this, and for C made, I want that. Okay, so now I have a dynamic formula based on this row, and if I copy that all the way on down, there are the numbers that were predicted. And I can also see how far off I was. I mean, it looks like eyeballing it, it looks like I'm off by a couple thousand from the actual cost based on my estimated formula. In almost every case, it's always in the 40,000s, so that looks good. Let's just see what my error, also called a residual, is. So equals my prediction less the actual cost. And so sometimes we're over and sometimes we're under, and on the whole we hope that our over and under estimates kind of balance out, so it's only off by like $31 when all is said and done across hundreds of thousands, if not several million dollars in transactions there. So that's good. Alright, now I don't want to make this video too long, so I'm not going to create a second model, but I'm going to demonstrate the approach for potentially creating an alternative model to this one. So one of the things I found here is that one of my input variables was not useful, supposedly, in predicting the outcome cost there. We weren't able to say that A matters. We are able to say confidently that B and C matter, but not A. And so what I'm going to do is I'm going to exclude this variable, kind of prune my model then, and see what happens. Now I have these numbers that tell me how well my model does, how well it performs. Let's see if it performs any better if I change things up a little bit. So my X range is now going to be just those two columns. And let me find a place to put this. Maybe I'll put it off to the side, because that'll make it a little bit easier to compare. Okay, so left to right, r squared. This one's 0.574, this one's 0.56. So which one's better? Well, a higher number is better, so that looks like this model's better in terms of kind of predicting the variances that happened in this outcome variable. Now let's go down to this f value. Over here, this f value is higher. So my new model actually looks like it's better, and this significance value is lower, meaning it's the probability has actually gone up that my model matters in this one, and that the outcome we got wasn't just by chance. And then in terms of the p-values, I only have b and c as input variables now, but the p-values are actually more significant. They're lower. So we know we're really sure at this point that these things matter. But by trimming off something, it looks like we lost a little bit from this perspective, but we gained something from this perspective. As you build your own models, you want to kind of mess around with this kind of thing. Oftentimes it makes sense to trim out variables, particularly when there's way too many variables in the model, because at a high number of columns of variables, it's actually detrimental to model estimation.